thanks everyone for being here. My name's Chris Hockley, Mike Bacula, it's Chris Samet, Chris Kirby, and Rajan Khatri. We're from EmbryRiddle University and the Autonomous Systems Lab, and today we're going to be presenting natural evolution in flight. First thing we had to do was define what the problem was. And as near as we could make out, the problem was getting an autonomous UAV, which was JAWS compliant, into a building, looking around that building, finding an object of interest, and then transmitting data from that object of interest back to the user. Doing all of this whilst being safe. From this, we started to pull system constraints. There are explicit constraints and implicit constraints. Among the explicit constraints were obviously the size of the vehicle, less than 1 meter, mass of the vehicle, less than 1.5 kilograms, then data link, including dB loss and bandwidths and such. Implicit constraints, transport, we had to be able to get it, the entire system, not just the vehicle, from where we are to where we were competing. We have to be able to manufacture the equipment in-house, or as best we can in-house, so we don't get stuck waiting for external vendors. And we had to actually be able to budget and use our resources effectively. As we're one of the few schools that's actually competing in every competition, we would pull everyone onto one project at the expense of others. So what we did was, after getting our constraints down and defining the problem, we had a brainstorming session where we went through and looked at all the different types of vehicles we could be using, from quad rotors to blimps to tail-sitting aircraft to 3D aircraft to one-winged helicopters. Got a little stranger than that, but not much. And then we had to develop a functional specification for these systems. So we went from a brainstorming session to pulling the functional specifications for that. From that, we selected 3 candidate vehicles and set up evaluation criteria which would be even to all of them, because obviously we couldn't expect to do a speed trial against a quad rotor, a coaxial, and a blimp, because the blimp is immediately handicapped because it's a large sail. Then we did something. Then we basically took that evaluation criteria to the fly-off against the vehicles. These were our candidate vehicles. We had a quad rotor, a thrust augmenting ejector or a turbo plant, which is basically a annular wing with a duct, and it sucks air over the wing to create lift. A coaxial helicopter and a monocopter, which we'll get a bit more detail about a bit later, because I don't know how many of you are familiar with monocopters. In the end, based on a couple of criteria which we can go into in questions if you want, including simplicity, price, robustness, and climb, the monocopter won, even though there wasn't a huge amount of data for us to develop from. The system itself actually developed from a Samara seed or a maple seed, which I'm sure most of you have seen. If you drop a maple seed, it will auto-rotate and spin. So all we did is take the maple seed wing, kept that, and the seed pod we replaced with brains and a propulsor. The first picture you see is actually our first successful test flight. We threw it off the side of the engineering building with the motor running, and it flew. You don't know until you throw it. So then ever more capable vehicles started to be developed, including vehicles that could rise off the ground, vehicles that could hover stably, which is one unique thing about this vehicle, and vehicles that could actually translate in any direction. This was incrementally moving towards our competition design, which allowed us to hover, move in directions, and locomotive basically. The component layout, again, the vehicle is actually, by design, incredibly sparse. Our entire vehicle weighs 180 grams, which is less than some sensors that are being used on vehicles. So we had to keep it sparse because we literally could not lift anymore. Most of the vehicle is the wing. Actually, it's a 21-inch long vehicle, 14 inches of which is wing. We have IR sensors which are mounted on the hub of the vehicle, which is the center of rotation. This provides some advantages which will be described later on. We have a control flap, which is bless you. A control flap. This actually allows the vehicle to move in any direction, which we've got video and some explanation of how that works a little later on. and the electric ducted fan, which this is the thing that actually provides the propulsion for the vehicle. After we got the actual airframe working, it then came time to turn it to an autonomous system, which, as I'm sure all of you are familiar with, means we have to close the sensor plan and act loop. And for this, I'll pass over to Mike Bacula, who will go into a bit more detail on our sensing strategies, our planning strategies, and our acting strategies.
So, for the sensing side, our key sensor is the sharp infrared ranging modules. There are 3 of them on board the vehicle. 2 of the medium-sized 180 centimeter range 20 to 80 centimeter modules, and 1 of the long 5 meter range modules. We read these multiple times. As you saw, the vehicle is a free rotor. The entire vehicle turns. There's no fixed portion of the vehicle. So our strategy with these sensors are to look at the sensor multiple times per rotation. That allows us to have, in essence, for the weight of one sensor, an array of that sensor, and that allows us to generate range data throughout the entire area of the vehicle. The reason we use 2 lateral sensors is because the characteristics of these infrared sensors is they have a minimum effective range, and we use the short range sensor to cover the minimum range of the longer range sensor. The minimum range of that short range sensor is actually within our wingspan, so we get complete coverage out to 5 meters. For the mission sensing, we use optical sensing. We have essentially it's a phototransistor. It's a non-imaging sensor with 2 filters over the front of it. One is a spatial filter called the reticle. We have a pattern where, again, using the vehicle's inherent scanning motion, we can look for point sources. We can discriminate point sources through seeing time patterns in the data. Basically we get a square wave throughout part of our rotation. That allows us to sense that something is there, and allows us to sense phase of the target in relation to where the vehicle is. To discriminate specifically blue LEDs, which is the target of interest for this mission, we use a 470 nanometer interference filter, which provides us with just 20 nanometers up or down from the blue. Looking at the available blue LEDs out there, we figured this was a good discriminator for just the blue LED. Now, we've talked about, both of these sensors are using the rotation of the vehicle to determine what direction we're seeing. The way we do that is we actually have a magnetometer on board. It's a Honeywell HMC 1052 analog magnetometer. We run that through an op-amp amplifier and then use one of the inputs and run that to one of the inputs on our onboard microprocessor. That allows us to have a consistent phase reference from rotation to rotation. And then using that, we trip an interrupt, we count the amount of time it takes to go around to the next interrupt, and that's our rotation phase reference. Everything that we sense, every time we read a sensor, reticle or the infrared sensors, we timestamp them in relation to this phase signal. Mentioning the computer, we're using, essentially it's an ATmega 328 based on the Arduino platforms, or an Arduino Pro Mini. This is a 16 megahertz 8-bit microprocessor with a C-based programming environment that all of our low-level routines are written in. That provides not only sensor integration, but we also do the low-level reactive. We'll talk a little more about the action strategy in a moment. But all of our low-level sensing and obstacle avoidance and mission completion criteria are handled on board the vehicle, as well as we then send some of the sensor data up a data link.